So I am, my background is geological. I basically studied how you build a planet, and I did that both on Earth and, of course, planetary-wise, using things like meteorites to understand again how you build a planet, where we came from, and in the end, again how things kind of differentiate into what we call the Earth. Before EDAX, I was at the American Museum of Natural History, where I worked as basically a curatorial assistant, so it's called a scientific assistant, basically helping a curator do his research, kind of control of basically a research kind of group thing there. While I was there, I actually bought EDAX system, did EBSD on meteorites, and then after a while, they said, "Hey, you seem to know what you're doing," and gave me the job of application engineer. So there's probably quite a few students on here. I'll kind of tell you again what I do, because it's kind of it's an interesting kind of career path that most people don't really think of. But my job is both post and pre-sales support kind of stuff, where I help you understand what the system can do to solve your problems, and then after you buy the system, I basically help you with anything that pops up after the sale, saying, "Hey, how does this work?" Training. Again, after kind of just making sure that you understand what the system is doing, what it can do for you, and in the end, again, we want you to get the best out of our product. So the more information you have, is good. And that's what this really kind of the point of this whole webinar over the whole next 2 days is to give you guys information to use this system the best you can. Because what I want you to do is I want you to use this system, understand how it works, and basically, get all those papers out there, get that information out there about all this awesome information you can get using the EBSD system. And that's again what I kind of, what I want to do with all this. Again, I'm open to questions during the actual talk itself. So again, feel free to, write anything you need, and go ahead and give me, those kind of questions. So the first talk today is going to be kind of this again, understanding the basics of EBSD indexing. I think it's important to understand how an orientation is basically figured out from the EBSD pattern. And after that, it is useful, to really understand. If you understand how it happens, how this actually we get the orientation, it helps you basically troubleshoot if something does go wrong, and also it helps you have more confidence in your data, because it's no longer a black box. It's no longer, oh hey, EDAX says this is the orientation I have. Instead, it's gonna be, oh hey, this is the orientation I have, and here's why I'm comfortable saying this. Because I'm going to talk about this in detail about patterns, and pattern quality, and kind of going from there. And don't want to get too far ahead of myself. So I'm actually going to start with the presentation. Kind of a little bit early from that, but I think we got enough people here. So understanding the basics of EBSD indexing. Oops, give me a second here. Here we go. So here's kind of the general outline of this talk for pattern indexing. We're going to talk a little bit about pattern quality, and then about image processing and why it's important for pattern indexing. We'll talk about the HUFF Transform and how awesome it is, and why it's really important, again, because it's actually how we find the Kikuchi bands themselves. And then how we determine the orientation from those bands, and talk about uncertainties that arise, and of course calibration of the system, again, to understand, again, hey, how am I actually doing all this? So comments on pattern quality. So if you ever look at any sort of EBSD literature, what you're usually going to see is these absolutely beautiful patterns. And I can show you pretty patterns all day. But these pretty patterns are not really needed for good EBSD indexing results. If you ever come to a training course, what I'm going to tell you over and over again is learn to trust the HUFF Transform, because the HUFF Transform is one of those things. When I got this job, I had to basically learn how to trust it myself. I had an older DigiView camera. It goes like 200 patterns per second. It's not very fast, which means you could got really, really good patterns. And when you get those good patterns, you feel good about your data. But as you go faster, your pattern quality tends to get a little bit lower. So you have to really trust the HUFF to find these lines. And sometimes you can be like, is that really a line? I'm not sure I believe it. But as you learn how to trust the HUFF and to get the ugly patterns to do a good job, you can collect better data faster. This is more true for the CCD-based cameras than the CMOS, and we'll talk about that kind of in the 1030 presentation. But ugly is indexable. So if I have an ugly pattern, it's usually, you'd be surprised. How low quality can you go? It does depend on the material and other things, but lower than most likely you're to believe me. Um, and that said, I'm going to try to convince you that again that ugly patterns work. And let's go ahead and actually show you some of these. So this right here are good patterns. If you showed me these, I would be like, oh yeah, these are all fine. And you can see as let me go ahead and find my little pointer here. Turn on my pointer, laser pointer. So here you should be able to see my pointer now. Here you can see this is
Hey,
a low noise
Shawn,
pattern.
real
Yep,
quick, I'm still just seeing the title slide.
interesting. So it says, what's going on here? Pause share, new share. It should, I'll just share my entire screen one and that should fix it. I was just trying to be a little coy and just show you PowerPoint, but go ahead and stop share. What's going on here? One of these days we'll figure out technology.
You figure we would by
PowerPoint.
now, but it never works for some reason.
So this shows. So there you go. There should be seeing why do we show pretty patterns?
Yep, that's it.
Is that what you guys see now? Cool. Yeah, I was trying to just show the PowerPoint slide itself, and apparently that just didn't work. So I was trying to have like everything open with the chat questions and PowerPoint slides and all that good stuff. But cool. So right now I can't see chat, so just keep that in mind.
Okay.
So if there's something to pop up, I'll have to kind of just yell at me. But so let me go ahead and get my pointer up now. And so yeah, here's me talking about that. And let's go ahead and now you should see patterns. So hopefully you guys see patterns now. And here again, we can see these patterns. And these are, this right here is a high quality pattern. I'll talk about gain a little bit here when we talk about the Hikari, but the Hikari, you can add basically noise to the pattern, which go a little bit faster. And as you can see, as I add noise, the camera goes faster, the pattern quality gets worse. To the HUFF Transform, which is kind of the first real big step in doing EBSD quality indexing, all these patterns are more than fine. You can see you can see all these lines here. The computer has no problems at all seeing those. But now I'm going to kind of start pushing, a little bit of disbelief on you guys here and say, hey, this pattern here is perfectly fine as well. Now, again, it's going to be somewhat material dependent, but you can see here that this is on a properly prepared sample. I have information here. This is enough information to actually get a fully indexable map. So here you can see that there's hints of lines here that you can kind of see. That's good enough for the computer to do. So here you can see that this is, here's a pattern from this map over here on the right. You can see I'm dropping a little bit about grain boundaries here, and that's going to be kind of what's going to happen if you do this kind of thing. But this is easily going to get over 99% indexing with pattern quality that bad. Now, again, you're going to start not believing me more when I kind of show you patterns that look like this. So this is using what's called NPAR. NPAR is a pattern algorithm we have that basically just does what I call spatial pattern averaging. But in the end, you can see down here, if you guys look at B, C, and D, I'm not sure you're going to believe me. And this is where, again, I think you have to do your own experimentation to understand, again, how bad patterns can be to actually get this. Now, the key thing here is that while these patterns are bad, there still has to be information in them. So your sample's not prepped properly. There at least has to be some sort of pattern information to be had for the system to actually see it. But again, you can see down here, like on C and D, there's no information here that you guys can see, but the computer can actually basically fully index this material. It can do a good job on the fly, but post-processing wise, it can do even better and basically get you a perfect map. Again, there's real no differences here between A, B, C, or D with the final product. But again, this is again, you have to really learn how to trust this HUFF Transform. So really what you need to think about is, again, EBSD is kind of this machine vision of saying, okay, I can see information in this pattern. Why it's less visibly appealing to us as humans to look at a blurry kind of blob versus a nice crisp pattern. Basically, all it really matters is what the HUFF sees. If the HUFF can see it and get the lines correctly, it's going to provide accurate results. And this is, again, kind of that learning curve of you believing this or not. Again, there are some caveats on this. You have to have, you usually have to have information. The patterns can be bad, but there still has to be information in them to be had. If there's no diffraction, there's no information, there's nothing to index. So it's just gibberish. But again, if there is information, it's good to go. Some references from this talk. A lot of this goes back to the early days of EBSD because They figured it out and it works very well. Some of this stuff is changing with some new methods of indexing, but the basics of indexing was really kind of figured out by Dr. Stuart Wright in his PhD at Yale back in the day. So here you can see here's some automatic analysis of EBSD. Again, we should be very thankful for Dr. Stuart Wright, who still worked with EDAX, and he is, again, his PhD was basically the one that figured this out. You go down here, again, you can see there's some more about the HUFF Transform. The HUFF Transform is an incredible tool for finding basically line detection in images. There's a lot of good YouTube videos out there on the HUFF Transform. So if you're really interested in how what's called the HUFF or the radon transform works, that information is out there. I'm going to talk a lot about this composite index approach that we use, and this is really, really important for understanding how well you can be comfortable that your data is getting something correct. And again, it's an incredibly powerful sort of tool. And of course, we have other things like phase differentiation and other things that can be useful. So what's our general geometry for this? This is an older system here, but here I have my my SEM column. I have my sample. My sample is tilted to 70 degrees. I basically go ahead and take the image. I diffract through my sample. I hit it on a phosphorus screen. The phosphorus screen lights up, and I take a picture of it. In the end, those bands are basically a representation of the reflecting lattice planes of the sample from the actual crystal volume that I'm diffracting through. So I go ahead and get that. I get an orientation, and ta-da, I have an EBSD map. So what I do with the pattern then is I could basically do this by hand. If you really hate yourself, you can go ahead and figure out all this information by yourself and say, okay, this is a 101 axis. This is a 111 axis. What's the angle between these? What's my orientation? And ta-da. Luckily for us, again, computing power is much easier nowadays, and because of that, automated methods can find these faster than you. No offense to any of you, but they can actually do it better than you as well. So these algorithms exist that again can kind of do this process for us, and again, we should be thankful for that. Back in the day when this all kind of started, most of the PCs were doing less than a pattern per second, and again, now we're doing over 4,500 patterns per second. So we should all be very thankful that computers are awesome. Now, again, these are nice, pretty patterns here. You can see they're relatively flat field. There's no real kind of big gradients in them. They're just kind of patterns and what we expect an EBSD pattern to look like. But in reality, your EBSD pattern is basically two things to superimpose on top of each other. What it is a general background signal and your patterns. And this is pretty common here. You can see that this right here is your raw pattern. Raw patterns tend to be weak. So you can see the lines, but you also can see it's a very strong gradient that basically overrides that. That's your background. So whenever we do EBSD, what we usually do is we take the raw pattern, we take some sort of background. In the end, I get a better contrasted image that allows the computer to do a better job of finding the lines. Now, again, the HUFF can actually find lines on this unbackground corrected image, but it's a little bit harder for it to do, so it takes more time and can get worse results. So we take a background, we subtract that background, pretty picture. Now, this background part is honestly one of the issues that most people will mess up. You always want to make sure that the background, when you take it, is going to be on a basically representative area of your sample, but over a large area of different grains, because I'm basically trying to blur and average things out. If my sample has a strong texture, I need to be aware of that, and I might have to do something different for the background. I'll talk about that next slide. Also be aware that, of course, you want to make sure it's sample. You don't want to be going into free space or onto the edge of the sample if possible, because those can actually put artifacts in the background itself. Now, if you do have like this single crystal or rough samples or textured samples, we can do a different kind of filter, we call dynamic background, which basically blurs the pattern itself and uses the pattern itself as its own background and lets you get what you need to do an EBSD pattern. Now, this right here is what you usually see with an EBSD pattern. Again, nice and flat field. And you can see here that it's a nice dirty phosphorus screen because, hey, phosphorus screens do get dirty or damaged over time, and that's kind of what they do. So again, computer doesn't really care about these, they're just there. And you actually can stack these backgrounds on top of each other. There's a whole bunch of things you can do with the image processing of these patterns. You can spend days trying to figure out this kind of stuff if you really wanted to say, okay, I want a very, very specific background for what I'm doing. Overall, this image processing, you don't want to go too crazy on it, but you can go crazy if you want to. There are plenty of options for this kind of things. In general, again, this does slow down the process because you're adding extra steps. So just kind of be aware of that. In the end, it's really what you care about is can the HUFF find the lines off the pattern that you're giving it. And if you're just making it better to look good for yourself, the HUFF doesn't care. So how do I find these lines? And I've kind of already spoiled that a little bit, right? Saying, hey, it's this HUFF transform, because the HUFF transform is by far the most important part of EBSD data getting the orientation. So what the HUFF transform does is basically a mathematical transform that turns a pattern like this into this, and then we basically use an algorithm that finds what's the line. So in here we can see that and this dark like dark, dark like dark, these are lines. So this guy right here is probably this guy right here, this green guy. I'll talk about again how that kind of works. So the HUFF transform is basically an accumulator array of an EBSD pattern itself. I'm not going to get too deep into the math here because I'm a geologist. I just look at rocks, right? So I don't know all this math to a high degree here, but essentially it looks at it in what's called a row theta space. You go ahead and you start in the middle of the pattern. You change your row and your theta as you step through it. And you basically say, okay, this is a bright pixel, this is a dark pixel. And in the end, you get the image that you saw with the bright spots and the dark spots. And that's what we kind of do with this. So basically, you go through, again, every single pixel, you go through every theta and row you have. So in the end here, you can see that a line like this becomes a series, basically what happens to do a series of these sinusoidal curves. They all hit and basically what makes a hot spot, but also a dark spot. So we have a dark, light, dark, and that's what we're going for when we're doing EBSD. And here's kind of a thing here. This is technically an accumulator array. So again, I do point by point by point by point, and I get a spot. This works on basically almost any kind of image in general, where you will basically be able to find lines. Again, it's used from everything from like LiDAR systems to nowadays they even use it for Tesla's car kind of things. Use this kind of transform to understand what things are by looking at the shape of them. Again, we use it to find lines. HUFF transform can also be used to find circles or whatever else you want to find. And again, in the end, and you kind of get this little what we call the butterfly kind of a look for a true line in this kind of space. So again, here you can see kind of this color-coded aspect of the HUFF transform, where you can see that again, like this yellow guy here is this yellow guy over here. But in the end, again, light, dark is what the computer is looking for. It doesn't have to be very strong. So here I can see that this little bit more of this light blue guy over here. Actually, I think it's this one here. So I have like 3 different blues on here. Should be this guy here. Here's this guy over here. Here's this big white line. Is this over here? And you can see they're not even symmetrical. But again, they're just kind of finding the middle of the line. And this is really what we want to see here is, hey, how well the HUFF is doing. How well the HUFF is doing is going to be something that, when you're understanding and troubleshooting something, you should be looking at. So here again, you can see the HUFF. We want it to be in the middle. We want to make sure that these zone axes are well defined and kind of nailing it here. And again, we're good. We're not cutting across the lines or anything like that. We're actually right in the middle, and all the intersections kind of make sense. Again, if you start getting a little bit higher or lower here on the HUFF, these lines will move a little bit more to the edges, and that can affect the indexing itself. So much like the patterns themselves, the HUFF transform could use a little bit of help with the contrasting. So we do what's called a butterfly mask after it. So we go ahead and do the HUFF transform, and then we do this butterfly mask, which basically makes this dark light dark pop out a little bit stronger. Again, I wouldn't worry too much about this. The only time you would change this mask is when something causes you to need to change it. So in general, this mask again kind of tells it what level to look at this dark light dark feature, and again kind of makes it pop out. By default, the system uses this mask on this 9x9 thing, and that's just basically again the kind of scale it's working on. The only time this mask needs to be changed, and I'll talk about this in the afternoon a little bit more, is if it's having problems. When it's going to have problems is usually if I have a an incredibly either low Z material, or I'm using either like incredibly high or incredibly low KV beam. So if I'm using a very low KV beam, my bands actually get very, very wide, and because of this dark light dark structure gets kind of a little bit fuzzier. So it gets a little bit dark, and there's more of a gradient this white big gradient, and then it goes where you know that dark gradient. But in general, this 9x9 really does a good job. If I do have to change this mask, it's probably because of some weird things. Recent examples of where I've had to change the mask is again, I've been doing some low KVA work with the clarity. Definitely I would use it for that kind of thing, or like I was doing graphite, where again, very low Z material, the band structure is a little bit different than most materials, so I could change this masking kind of a parameter that kind of helps me find the lines a little bit better. One of the other options in the HUFF is going to be what's called the Theta Step. The Theta Step is going to be, honestly, it's a rate limiting step for most indexing kind of things. The reason is because when you draw the HUFF, this Theta Step is basically your pixel density. So I talked about the HUFF being in row theta space. Well, this is a theta. And what it basically happens here is my pattern, I'm stepping through the entire pattern in 1 degree or 3 degree increments, or 2 degrees or half degree or whatever. But basically it's making this density of this, these curves either more or less. And I got to tell you, in general, this 1 degree versus 3 degree versus 2 degrees or whatever doesn't make that much of a difference in the orientation precision because it's still finding the line. So again, you can see it gets more pixelated, but it's still going to put the pixel right there versus, maybe in the same pattern, it's going to put it, essentially the same spot. So this theta step is basically, how much computational power do you want to use to make the HUFF transform? Just kind of getting a little bit ahead of myself here, but for the fastest speeds and the velocity, the theta step has to be 2. It has to be 2 degrees because again, it's just so computationally heavy to be doing this theta, this kind of accumulator array, that the computational power just goes up very quickly. And because of that, we're actually ahead of computers. The computer for velocities are incredibly strong. And with that in mind, you have to actually do less work because it's even too much for top of the line computers. One of the other things, honestly, is no longer the rate limiting step, is what we call binning the HUFF. So you can bin down the HUFF as well, and it will do an okay job. This is honestly, I could probably remove this slide. It's just not used anymore. The computer speeds are basically high enough that this is not really a rate limiting step. It's really is the theta itself. So this is, again, you can bin the HUFF to such a kind of degree. It does matter somewhat, again, with some of the older materials, because you'd match the HUFF binning to the camera binning, but in this case, it doesn't really matter anymore to me because it's just not the rate limiting step to the computers. But again, if you do have an older DigiView and have an older system, which I think you guys have a DigiView laying around, but I don't think you have it actually hooked up right now, the DigiViews, you really should match the binning and the HUFF binning itself. So here you can see I have a full pattern. I should be using a normal binning, but if I do bin the pattern down, I should bin the HUFF as well. So HUFF has found the bands. What do I do with these bands is really kind of the next step here. So when I'm indexing, what I have to do is I have to build a lookup table. I then have to basically have a voting algorithm to say, hey, which one of these actually works the best? And then I have to have measures of basically metrics to understand how well I believe the data is. And it's what we call confidence index, or CI. The other one is this fit value. So first step, building the lookup table. So the lookup table comes from those phase files. So the first thing you're going to do with EBSD is you are going to, you're going to open up your sample. You open up their software. You're going to put your sample in, and you're going to say, okay, my sample has, X, Y, and Z phase, and for each one of those phases, those phase files had information in it about, okay, which bands do I expect? What is my symmetry? And what is basically the angle between those? So I go ahead and look and say, okay, I can expect the 2, 0, 0, the 1, 1, 1, and I can basically start making all the symmetrical pairs of these. I can basically say, okay, here's what the angle between these pairs, and in the end, I throw the duplicates out. So I'm basically saying that I expect in my sample between the 1, 1, 1 and the 2, 2, 0 plane for there to be a 35.3 degree angle. And I say, okay, but between the 2, 2, 0 and the 2, 0, 2 phase, there's going to be a 60 degree angle. So you can see now I'm actually just starting to get a lot of different iterations here of all these different angles between all these different planes. And I look at my pattern and go ahead and skip that slide. I can go ahead and look at my pattern and say, hey, what's going on? Okay, here's my pattern. Here's my HUFF line. And it says between this guy and this guy here, my 200, my 311, I have a 72.5 degree angle. Between the 200 and the 111, I have a 54.7 degree angle. And over here, I have a 58.5 degree angle between the 111 and the 311. And based off of what we call this triplet here, I can go ahead and say, oh, hey, I have an orientation based off of this. But there has to be some wiggle room here. So what we do is we use what is called this interplanal angular tolerance value. For this example, it's going to be set at 5. The software by default does it at 3. And I would tell you never, ever, ever really no need to change this. So I just want to do some quick thing here. Has there been any questions in chat so far? Again, I can't really see the chat, so I just want to make sure that, let's see, can I bring up the chat somehow?
No, I haven't seen any questions yet.
Okay, cool.
I can stop you if there are.
Yep.
And yeah, if anyone has questions, just ask any questions. I think Shawn loves questions.
Yep.
I think it helps everyone out a lot.
Yeah. So yeah, it gives me good feedback of making sure that I'm understanding things, that I'm doing a good job explaining things. There are questions that makes me it's good feedback for me basically. So here we can see this is I've now opened this angle up by 5 degrees. So now instead of this being 54 plus 0.7, it's now basically a range here. So now I can say, oh, hey, this angle here could actually be the intersection between the 311 and the 311, or basically any of these other ones here in this red box, or this blue box, or this now. So now I suddenly have multiple solutions that exist for this triplet. I have to have a way to do this. Now, this is a good time to actually say, we're not just using triangles here. A triplet doesn't have to be a triangle. It's just basically any 3 intersecting lines, but triangles are just easier for most people to visualize. Okay, now it's being feisty, not letting me change my slide that way. Okay, what's going on? Good old technology. There we go. So here we can see here that I basically have the lines here. I now have 3 solutions that are very, very close. And you can look at this and say, okay, which one works the best? So this right here is my triplet solution. I can say, okay, let's see, how does this look? Okay, it's in the middle of the band here. We're doing a good job. All these other bands look to be doing a relatively good job. I go over here to possible solution 2. I can say, okay, the zone axis is a little bit off here. Okay, this is nailing this line pretty much in the middle. This is also a little bit off. Go ahead and look at solution 3 and say, okay, look, yep, blue guy's nailed. Red guy's nailed. This guy's pretty far off. This guy over here is pretty far off. So in the end, you can say, which one of these is really going to win? So again, what we do is we actually vote for each solution, and we say, okay, how well of a job does it do, basically on fitting these? Now, the number of these solutions is going to be based off of how many triplets I'm actually basically looking at. It's going to be based off how many bands I'm using for this. So when you're doing the HUFF, by default, you're using about 8 lines. So if you go over to what's called the HUFF tab, you click on the HUFF, it does around 8 lines. If I do 8 lines, it's going to have basically 56 triplets it looks at and is voting on. Most work is going to use between 7 and 9 lines for indexing this. This tends to goes up depending on if you're doing lower symmetry material. So again, I'm a geologist. A lot of you guys are material scientists, so you guys kind of cheat a lot and just do cubics. Cubics really just need 7. 7 will give you a unique orientation solution for most cubic materials. If I go to lower symmetry materials, again, I usually need more. If I'm doing a hardcore geological sample with a lot of phases, I tend to use 12. And then I get a much more solutions, but it's also much more computationally heavy because I'm doing 12 bands for each HUFF, which means I now have to do this triplet solutions for, put 12 in here for the math. You can see this goes up very quickly. So in the end, basically all we do is say, hey, does this work or does it not? And basically put a check mark in it. So here, again, I had solution 1, basically hit all the check marks for all these different triplets because I had 10 votes. Solution 2 did not hit it, so I had 1 vote. And then solution 3 only also had 1 vote. So here we can see that, hey, these may not be the best for this guy. Solution 1 wins, gets the most votes, right? I mean, today's January 6th, right? So we can make a joke here about, the most votes wins. And in the end, here is the solution, and you can see that, again, all 5 bands matched. We get a very low fit value. This fit value is basically a deviation between the index solution and the actual pattern, is what we found the lines to be. So again, it's kind of a deviation. If you're a user for one of our competitors, they also call this the mean angular deviation, or the MAD. So here we can see a low fit value. We're nice and good. Everything's in the middle. This is a correct solution. Now, the other reason I can know this is a correct solution is, again, the HUFF rate here is only using 5 lines, right? So it's not using this line here. It's not using this line here. But the orientation solution that I got is using this line. So here you can see that this line is being used. These are being basically where they need to be. Well, again, they're not actually being used over here for the HUFF. So the orientation was found without using these lines, but hey, these lines are here. I should start feeling pretty confident that this is the right solution. Again, here is the solution 2. Again, you can see it's cross-cutting across here. This band is missing. This is a bad solution. The fit goes up. And again, this is the fit is this kind of this average misalignment between the detected bands and the recalculated bands. Now, in general, this fit value can be very useful to understand the quality of my data. So here's a fit value of 0.2. This right here is a fit value of 2.0. I will kind of give you a little bit of hint here later on. Kind of keep this in mind. Notice how this pattern is close but not quite. This fit value is a little bit high. There's a reason for that. And I'll kind of talk about that for later. But fit value, again, the deviation between the detected bands the HUFF found and what the orientation solution found. So I did this voting. We had this idea of what we call confidence index. And again, this is unique to EDAX. But what it basically is a measure of uniqueness of solution. So what we do is we say, okay, I had a total of 10 votes. I'm going to go ahead and put that in my denominator here. And then I'm going to say, what's the difference between my first best solution and my second best solution? So here I have 10 minus 1 divided by 10 gives me a CI of 0.9. Now, what does a 0.9 value mean? Well, basically saying that, hey, I have a very unique, I have a very big jump between my first best solution and my second best solution. I should feel pretty confident that I got the right index in here. But how good is a 0.9 value? Well, here's the slide I always show to say, hey, how good is a 0.9 value? And I always ask people in this case, I would say, hey, where is this on the chart? And I'd be like pointing up there. And if I was giving this in real life, in an auditorium, you'd be like, okay, where's 0.9? Okay, well, here's my axes here. I have fraction correct on the Y. Over here, I have CI, and I go from 0 to 0.1 to 0.4. So 0.9 is somewhere off my screen on my third monitor over here, way over here on the right. So I can say that you can see that there's some breakpoints on this CI graph that I should really kind of understand. So at a CI of 0.9, I'm basically asymptotic around this 1. So it's saying, hey, I have a correct solution. I feel very confident I have this correct solution. At a 0.1, you can see that it's close to around 90%. So that 0.1, let me go back real quick. So 0.1 in this case would be, there's 2 different ways to do it, right? So 0.1 would be basically 10 minus 9 over 1. So if I had 9 solutions for my second best solution and 10 solutions for my first one, 10 minus 9 would give me 0.1. The other way, of course, I could just have one solution and then another one would be 0 would be the other way to do that. So here I can say, okay, I have 0.1. Even at 0.1, I'm still 90% correct. If I look at 0.2, I'm basically asymptotic. So even at 0.2, the 0.2 value means that I have 8 solutions here. So 10 versus 8. And again, I feel very confident with even just a 2-vote difference that I have the correct solution. Now, in fact, if I look over here at 0 CI, I'd have about 40% correct. So even if I had no difference here, I can say, hey, this is this. Now, you can fake out the CI in a couple different ways. I can do a map, and I'll probably actually do this in the afternoon, where I'm always going to have a 0 CI. Because this is going to be based off of the voting algorithm. So this voting algorithm is not just doing solutions based off of orientations, it's also doing it off of phases. So if I have two phases that are essentially the same, it's going to build the same lookup table based on those phases. So I get the same solutions, which means my first best and my second best solutions are going to be the same. So if I take x minus x is always going to be equal 0 divided by 10, it's always going to be 0. So again, anything you actually ever do will always kind of push the CI to be a lower value than it should be. So again, even at 0.1 and 0.2, you should be very comfortable that the CI is doing a very good job. If you're using a 0.3 and higher range, you should be very, very comfortable that it's doing a good job. If it's down in this 0 to 0.1 range, you should probably understand why it's not doing so good. And I'll talk about troubleshooting the CI a little bit in the afternoon. Now, part of the reason the CI does go down sometimes is because EBSD, the patterns are based off the interaction volume. The interaction volume goes across the grain boundary. You're into two grains. You have two diffracting volumes. You have two patterns superimposed on top of each other. So we call it convoluted pattern. This voting algorithm that we use is got something that is incredibly powerful. Which kind of, I don't know back in the day if it's just luck or what, but it does a very good job of deconvoluting patterns. So here you can see, here's my electron beam. It's interacting with my tilted sample. Because we have a tilted sample, it's very easy for this teardrop shape to go across the grain boundary. Because of that, you can see that I either can be in the blue or the red grain up here, or I can be a mixture of the two. And this is pretty common to actually can see this. I can do this on the microscope sometimes, depending on what you're looking at. You can see that, hey, I have a convoluted pattern here, but in the end, I can still actually get a same orientation, a correct orientation off of that. How well of a job does it do? Well, this is a good example of this. So here is what we call an IQ map. An IQ map is basically how much information is in the pattern itself. So here you can see that I have a grain on top, I have a grain on the bottom. Here's my grain boundary. You can see that it has less information in it. Why does it have less information? Because because you're blurring the information when you put two patterns on top of each other. Now, if I look over here at what's called the orientation map, I can see that if I go right up to the boundary, and it skips orientation right over. So I can say, hey, it's doing a really good job all the way up to the grain boundary and even on the grain boundary, and then suddenly it switches over. So when I do that, you can see my CI goes down. So my CI goes down, 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 down. It actually gets close to 0 right on the grain boundary, and then it goes back up across the grain boundary. And that's because the convoluted pattern is finding the wrong lines. Because it's finding the wrong lines, it's basically, there's more check boxes to go around. So there's more check marks, so I get more lines or I get more votes. And so when I take A minus B, A and B are both relatively high, which means the CI is going to be, in the end, lower. So again, but it does a good job all the way up to the grain boundary. And that's kind of one of the nice things about this index inclusion. The angular resolution of the HUFF transform and the indexing routine is relatively high. You can do this experiment yourself relatively easily by just putting in a single silicon sample, doing a map over it, and then doing basically a misorientation angle across it. This is one of those things where you get better results the careful you are, but in general, the orientation solution degrees is going to be around less than 0.1 for most materials. So again, just be realized that if you're trying to do extremely high angular resolution EBSD off of what we call normal EBSD mode, you can get relatively high degrees of precision here. And of course, it does decrease with bending a little bit, but not that bad. Basically, just realize that again, if you do kind of bend down the HUFF, you are losing a little bit of precision in your angular orientation because you're basically just not as precise anymore. So there's a little bit more wiggle room because of that. So again, if you do bend things down, there are you can use a little bit here, but again, it's going to be tiny. So here you can see that the orientation spread with this is going to be maybe half a degree if I bend things down to extreme levels, and you can bend things down to extremely crazy levels, and I'll show that later. In general, again, this is going to be based off of what we call the reflector list. I'm not going to get too deep into this kind of stuff at this point, but this is what's built basically in the phase files. There's mathematics behind the phase files. You build a phase file. You put in where the atomic positions are. There's mathematics to say, hey, how strong these are going to be next to each other. And there are some differences between X-rays and EBSD, like XRD kind of stuff, but nothing that you really should worry about at this level. That said, there's are going to be some times where you do have ambiguities and EBSD and angular resolution kind of stuff. So this right here is, I think, a good example of this, where I have 3 different solutions here, and you can see that they all pretty well work. If I have this in a map, I'm going to have this kind of a speckling thing going on here. So here I can see that these speckle back and forth, and that's because the orientation is basically very close to being the same with different solutions. What this means is that, again, for some samples, the speckling will occur. Where is this common? This is most common in materials that is basically very slightly tetragonal. So if there's any steel people out there, you can tell me that, martensite is again, just basically a little bit tetragonal. Depending on this, again, the C to A ratio, you can't really tell the difference between a C axis and an A axis. And that's an open problem, really, in the EBSD community. I'll tell you that dictionary indexing does a better job at that. And that's one of the reasons I think people are pushing dictionary indexing so hard, is that it does help get rid of some of these ambiguities that traditional indexing can see like this, where, hey, I can't see a difference between these 3 patterns, because these 3 orientation solutions, because there's not really anything. It's within my precision. So all of these patterns and all this work is really going to be based off of what we call the calibration. The calibration for EBSD is basically just working off of what we call the pattern center. And I'm going to be a little bit sloppy here, so if there's any diffraction experts or EBSD experts here, I'm going to use the pattern center and going to kind of lie, but don't yell at me too much. And basically what the pattern center is where the pattern first basically hits the phosphor screen. So here's my electron beam, I diffract out, and then from there I radiate out as a sphere, and I hit my screen, and then I kind of radiate out from there, right? This is what's actually the source of the gradient you see with an uncorrected EBSD pattern. Remember how it's brightest here and then it kind of goes out? Well, depending on where my pattern center is, that brightness actually moves. So when we're doing EBSD calibration, for me to understand the orientation relationship between these bands, to understand the orientation relationship between my phosphor screen, my sample, and my column. So what we do is we basically take a pattern and we can go ahead and basically figure out what the pattern center is off of that pattern. And we do what's called an X star, Y star, Z star calculation off of this. And all this to basically do is we do this at different working distances. And if I do that, I can see how the X star, Y star, and Z star changes with my working distance. So the X star is going to be basically how far in my phosphor screen the pattern center is. The Y star is honestly the one that usually matters the most, because it's going to tell me, again, where the pattern center is on my phosphor screen. This is the one that actually changes the most, usually, with working distance changes. This Z star is basically my scaling factor. So if I got closer and closer to my sample, so I kind of zoom this in a little bit, my Z star would increase. I would get more information on this, but of course it gets a little bit tricky as you get too closer and closer. If I get further and further away, I get less information, and because of that, this is Z star value. I basically get, basically kind of zoom in, so to speak, on part of the phosphor screen. So I have to actually know the scaling factor. Here again, you can kind of see this as I change the working distance here to be shorter. This goes up, changes to go longer, it goes down. And based off this, we basically make 3 curves, and then we can read the working distance off the microscope, and that's how we kind of do this. In general, you don't have to worry too much about calibration because the geometry is relatively fixed. So what a calibration basically doing is finding the geometry between your pole piece, your sample, and your actual detector. In the end, the only real variable here should be where your sample is, and that's what we're basically doing the calibration curve for. Your detector should always basically be always in. This is not always true. I'll talk about that a little bit about apex. And here we can see my pole piece. If your pole piece moves, you have a big problem. So if your pole piece moves, well, yeah, let's go ahead and call service and say, oops, something bad happened. But here again, it's really a question of, is my detector in all the way? With Apex, we added the ability to basically change this a little bit, where I can say, hey, my detector is not always in all the way. Let me go ahead and use a different calibration. Really, honestly, the main thing that works with this is the calibration itself. You guys shouldn't have to worry about. The only real time I play around with calibrations is if I have a really big sample, my detector's not all the way in, or just something's wonky in general. As a general user, again, you don't have to worry about calibrations. The way to realize that calibration is bad is going to be if there's a if all your fits are bad. So if you remember earlier on, I showed you a picture that has a 2-degree fit. that 2-degree fit is because it's miscalibrated. If you actually looked at that pattern, the pattern itself is basically a little bit too big. If I shrunk everything towards the middle, it would fit much better. That's that Z star. That's that scaling factor was off in that calibration. So that would be kind of being a little bit tricky there. So yeah, calibrations exist. You don't really have to deal with calibrations. There's actually the secondary calibration that's also done, and that's what's called the PC, not the PC, what's called the PC shift, the pattern centering shift. And this is basically just a secondary calculation done that says, hey, um, when I'm actually rastering over a sample, my working distance technically changes on a tilted sample. So again, if I went from here to here, my working distance actually changes. And because of that, my pattern setters does shift as well. So we do a secondary calibration on top of that. Usually more important at low mag work. So if you're doing low mag work, this PC shift calibration matters more. Again, in Apex, we've actually done this automatically. In Team, this is done manually, but we can go ahead and talk about that as well. And of course, here's just a pretty pattern of actually not even a pretty pattern at this point, but this right here is a single silicon crystal sample. Here you can see all the axes, and you can see the PC in this case is around here. In general, we try to make the PC for most systems around about 2/3 of the way up the phosphor screens, so right here, so you get the best data at, and you kind of can do that work and see where it is on your system itself. So with that is kind of what I got for pattern indexing at this point. Again, it's a lot of information in a very short period of time. So this is where I would kind of open up to questions.